Hurricane Ida turned into a monster thanks to a giant warm patch in the Gulf of Mexico, and this is what happened. This is according to Nick Shea, professor oceanography, University of Miami, on The Conversation. As Hurricane Ida headed into the Gulf of Mexico, a team of scientists was closely watching a giant, slowly swirling pool of warm water directly ahead in its path. That warm pool, an eddy, was a warning sign. It was around 125 miles, 200 kilometers across, and it was about to give Ida the power boost that, in the span of less than 24 hours, would turn it from a weak hurricane into the dangerous Category 4 storm that slammed into Louisiana just outside New Orleans, August 29th, 2021. Nick Shea, oceanographer at University of Miami's Rosenstiel School of Marine and Atmospheric Science, was one of those scientists. He helps explain these eddies. Part of what's known as the loop current helps storms rapidly intensify into monster hurricanes. How do these eddies form? The loop current is the key component of a large gyre, or circular current, rotating clockwise in the North Atlantic Ocean. Its strength is related to the flow of warm water from the tropics and the Caribbean Sea to the Gulf of Mexico, and out again through the Florida Straits between Florida and Cuba. From there, it forms the core of the Gulf Stream, which flows northward along the eastern seaboard. In the Gulf, this current can start to shed large warm eddies when it gets north of about the latitude of Fort Myers, Florida. At any given time, there can be as many as 3 warm eddies in the Gulf, slowly moving westward. And when these eddies form during hurricane season, which is now, of course, their heat can spell disaster for coastal communities around the Gulf. Subtropical water has a different temperature and salinity than Gulf common water, so its eddies are easy to identify. They have warm water at the surface and temperatures of 78 degrees Fahrenheit or 626 Celsius, which is pretty warm for the water, or more in water layers extending about 400 or 500 feet deep. Since the strong salinity difference inhibits mixing and cooling of these layers, the warm eddies retain a considerable amount of heat. When heat at the ocean surface is above 78 Fahrenheit or 26 Celsius, hurricanes can form and intensify. Kindly support my Patreon account since YouTube has again demonetized my YouTube channel. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below. The eddy that Ida passed over had surface temperatures of a whopping 86 degrees Fahrenheit, that's 30 degrees Celsius. That's like a warm bath. How did you know this eddy was going to be a problem? We monitor ocean heat content from space each day and keep an eye on the ocean dynamics, especially during the summer months. Keep in mind that warm eddies in the wintertime can also energize atmospheric frontal systems, such as the storm of the century that caused snowstorm across the deep south in 1993. To gauge a risk this heat pool posed for Hurricane Ida, we flew aircraft over the eddy and dropped measuring devices, including what are known as expendables. An expendable parachutes down to the surface and releases a probe descending about 1,300 to 5,000 feet below the surface, so that's pretty deep. It then sends back data about the temperature and salinity. This eddy had heat down to about 480 feet below the surface. Even if the storm's wind caused some mixing with cooling water at the surface, that deeper water was not going to mix all the way down. The eddy was going to stay warm and continue to produce heat and moisture. That meant Ida was about to get an enormous supply of fuel. When warm water extends deep like that, we start to see the atmospheric pressure drop. The moisture transfers, or latent heat, from the ocean to the atmosphere are sustained over a warm eddy, since the eddies are not significantly cooling. As this release of latent heat continues, the central pressures continue to decrease. Eventually, the surface winds will feel the larger horizontal pressure changes across the storm and begin to speed up. That's what we saw the day before Hurricane Ida made landfall. The storm was beginning to sense that really warm water in the eddy, and as the pressure keeps going down, storm gets stronger and more well-defined. When I went to bed at midnight that night, the wind speeds were about 105 miles an hour. When I woke up a few hours later, checking on the National Hurricane Center updates, it was 145 miles per hour, and Ida had become a major hurricane. Is rapid intensification a new development? We've known about this effect on hurricanes for years, but it's taken quite a while for meteorologists to pay more attention to the upper ocean heat content and its impact on the rapid intensification of hurricanes. In 1995, Hurricane Opal was a minimal tropical storm meandering in the Gulf. Unknown to forecasters at the time, a big warm eddy was in the center of the Gulf, moving about as fast as Miami traffic in rush hour, with warm water down to about 150 meters, about 400 feet down. All the meteorologists saw in the satellite data was the surface temperature. So when Opal rapidly intensified its way to eventually hitting the Florida Panhandle, it caught a lot of people by surprise. Today, meteorologists keep a closer eye on where the pools of heat are. Not every storm has all the right conditions. Too much wind shear can tear apart a storm, but when the atmospheric conditions and ocean temperatures are extremely favorable, you can get this big change. Hurricane Katrina and Rita, both in 2005, had pretty much the same signature as Ida. They were over the warm eddy that was just getting ready to be shed from the loop current. Hurricane Michael, 2018, did not go over an eddy, but it went over the eddy's filament like a tail as it was separated from the loop current. Each of these storms intensified quickly before hitting land. Of course, these warm eddies are most common right during hurricane season. You'll occasionally see this happening along the Atlantic coast too, but the Gulf of Mexico and Northwest Caribbean are more contained, so when a storm intensifies there, someone is going to get hit. When it intensifies close to the coast, like Ida did, it can be disastrous for coastal inhabitants. What does climate change have to do with all this? We know global warming is occurring, and we know that surface temperatures are warmer in the Gulf of Mexico and elsewhere. And when it comes to rapid intensification, my view is that a lot of these thermodynamics are local. How great a role global warming plays remains unclear. This is an area of fertile research. We have to be monitoring the Gulf's ocean heat content for more than 2 decades by comparing the temperature measurements we took during Ida and other hurricanes with satellite and other atmospheric data. Scientists can better understand the role the oceans play in the rapid intensification of storms. Once we have these profiles, scientists can fine-tune the computer model simulations used in forecasts to provide more details and accurate warnings, and in the future, what will happen. This is by Miriam Frankel, Senior Science Editor on The Conversation, Creative Commons. Please leave your comments. Thank you for your support.